Good morning. I am Ravi Anand and here to present our work titled Evaluation of Quantum Cryptanalysis on SPECK. This paper has two parts. First, we estimate the resources required for key recovery using Grover's exhaustive search. In the second part, we estimate the resources of implementing differential attacks on SPECK. SPECK is a family of lightweight block ciphers released by NSA in 2013 and it has 10 variants. The different variants of SPECK are denoted by SPECK 2n by mn, where 2n represents the block size of the variant and mn is the size of the secret key. Here n can take values from 16, 24, 32, 48 or 64 and m from 2, 3 or 4. For each combination of mn, the corresponding round number t is adopted as shown in this table. The state update function consists of bitwise XOR, circular shifts and addition modulo 2n. The state of the cipher is updated as shown in this figure, where ki is the round key. The round keys of SPECK are generated using the state update function. If the secret key is this k for m is equal to 2, 3, 4, then k0 is used for the first round and the key ki for further rounds are defined as given here. Quantum implementation of XOR, rotation and addition modulo. XOR can be implemented using the C0 gates. Rotation can be implemented by using swap gates across wires, which requires 3 C0 gates. However, this can also be done by simply keeping a track of the necessary free rewiring, and so in the estimations, the swap gates are considered free. Addition modulo 2n, we use the circuit constructed by Takashi et al. As it uses no ancillas. This circuit uses 2n minus 2 Toffoli gates and 5n minus 6 C0 gates. Here we present some schematic diagrams for different operations which will be exploited later. Add implements b is equal to b addition modulo a. RR alpha rotates a right alpha times. RL alpha rotates a left alpha times. And Rx beta rotates b left beta times followed by a XOR with a. Now the quantum circuit for a key expansion. The key expansion routine is defined as this. So for m is equal to 2, we have two keywords K0, L0. K0 is used for the first round encryption. The circuit for further round keys is described as given here. First, L0 there is a rotation of right rotation on L0, then K0 is added here. Then the round constant is added to L0. This becomes L1 now. This L1 gets as added to K0 and we get K1. In the same way we get K2, K3, K4, where R, C, I are the round dependent constants. So for m is equal to 3, we have three keywords K0, L0 and L1 each of size n. And for m is equal to 4, we have four keywords K0, L0, L1, L2 each of size n. The round keys for the further rounds can be computed as described in this figure here. This is for m is equal to 3 and this is for m is equal to 4. We implement a toy version of the SPECK key expansion of SPECK with two keywords in IBM Q interface. The value of alpha and beta is assumed to be 1. The size of K0 and L0 is 3. The measurement of K0 after this implementation will give the value of the next round key, that is K1. Now the quantum circuit for round update function. The round update function f is defined like this. So the circuit for this state update is shown below, where ki, li, ri represents the quantum states of size n for round I. So this K0 is the first key, the key that we have. This L0 is the plain text and this is the left part of the plain text and the right part of the plain text. So here is this RR alpha, this is rotated alpha times, then R0 is added to it, then K key is XORed in this, which is then added to R0 and we get R1 and L1 in this way, and we can proceed later. Here KE is the key expansion routine which is described above. The figure below is the IBM Q implementation of the circuit for one round of a SPECK-like toy cipher. The assumed state size is 6. The circuit here describes one round of the cipher. That is, if we measure L and R states, we would get the value of the state after one round. Now quantum circuit for the full spec is described. The input to the circuit is the key K with K0 and L0 for here, and the plain text is split into two halves L0 R0. The output of the circuit is the ciphertext LT-1 RT-1, where T is the number of rounds. Below is the circuit for M is equal to 2. Here U is the round update function and K is the key expansion routine. We construct a spec-like toy cipher to implement it in IBM-Q interface. We consider the key size and the state size to be 6 and the number of rounds to be 2. The value of alpha and beta is assumed to be 1. If the plain text is L0, R0, S0, 11 and 111 and the key is 110 and 010, then after 2 rounds the ciphertext will be 101, 101. So this is the circuit for our toy cipher in IBM-Q. This here represents the first state update, then the key expansion, and then the state. And when we measure this, we should get the value of the state after 2 rounds, which is 101, 101. Now the Grover's oracle. Let R pairs of plaintext ciphertext be sufficient to successfully recover a unique solution. We then need to design an oracle that encrypts the given R plaintexts under the same key and then compute a Boolean value which determines if all the resulting ciphertexts are equal to the given classical ciphertext. So given below is a construction for R is equal to 2. Here M1 and M2, M1 C1 is the first plaintext, M2 C2 is the second plaintext ciphertext pair. M1 goes through this encryption where K is the key and this output is matched with C1. Here M2 goes through encryption and this is matched with C2. If both becomes equal, then this bit is flipped. So we implement the Grover's algorithm for our toy cipher and we have assumed the secret key to be 110010. So this should be the output obtained due to the Grover. We assume that the plaintext ciphertext pair is M is this and C is this. Then the outcome of the Grover is, as we can see here, 110010, which was our desired key. Just to be sure, we again implemented it for a different plaintext ciphertext pair and obtained the same key. Now the resource estimation. We estimate the resources required to implement Grover's search algorithm as follows. One round of key expansion requires 6n minus 6 C0 gates, 2n minus 2 Toffoli gates, and I NOT gates depending on the round number I. One round of state update requires 7n minus 6 C0 gates and 2n minus 2 Toffoli gates. So T rounds of spec would require T round updates and T minus 1 key expansion, and so T round updates would require T into 7n minus 6 C0 gates and T into 2n minus 2 Toffoli gates, and T minus 1 key expansion would require these many C0 gates and these many Toffoli gates. So NOT gates will always depend on the number of the rounds. So using this, we find the cost of implementing all the spec variants as given in this table, and the cost of the Grover's oracle is given in this table where R is equal to ceiling function K by 2n. Then we estimate the cost of the Grover's algorithm with 2 to the power K by 2 oracle iterations as this. Now we study the quantum differential attack on SPECK. We study the quantum resources required to implement the differential attack on SPECK. Here we present circuits for two main types of differential attacks, the differential distinguisher and the last round attack, and then analyze the resources required to implement these on a quantum computer for SPECK. We know that differential attacks exploit the fact that there exists a pair alpha dash beta dash for a cipher E such that equation 2 exists. This pair alpha dash beta dash is known as the differential. So to find a differential distinguisher, we try to find a pair of plain text P and P dash such that P dash is equal to P XOR alpha dash, which satisfies this. If the cipher E is ideally random, obtaining such a pair would require 2 to the power n trials. But on the other hand, if E satisfies equation 2, the attacker will collect any 2 to the power P plaintext pairs such that P and P XOR P dash gives alpha dash, and with a very high probability we will find at least one pair of P and P dash which satisfies this. Whereas a quantum adversary will apply a Grover's search over the set of all possible messages of size n, and this algorithm will attempt to find a message x such that this satisfies, E satisfies this. Since the fraction of messages which satisfies the given trail is 2 to the power minus p, so it is sufficient to make 2 to the power p by 2 Grover's iteration to obtain the correct messages. So the Grover's oracle to find the distinguisher is here, this, where ENC represents decryption and DAC represents decryption. This operator compares the value of p dash with b dash and flips the target if they are equal. Now this is p here after this, and this is p dash here alpha after alpha dash, and if this p dash is equal to beta dash, then this gets flipped. So we implement this Grover's oracle for our toy cipher to obtain the plaintext pair which satisfies this distinguisher given here with for 4 rounds with p is equal to 2, and we obtain this. So let this output be p, so it is 0 0 1 1 1. Then p XOR is equal to p XOR alpha dash, p dash will be this much. The corresponding ciphertext after 4 rounds are this, and we can easily verify that c XOR c dash is equal to beta dash, which proves that the output of this Grover's is correct. We now implement the last round attack for key recovery. Consider that we have a differential alpha dash going to beta dash with probability p and in rounds r. Then we extract the keys for r plus 1 rounds, and the process to extract the secret key can be divided into the following 3 phases: collecting and filtering phase, subkey guessing phase, and brute force. So in the first phase, we apply Grover's over all possible set of the players of plaintext p and p dash, such that p XOR p dash is equal to alpha dash, and then we search for the pair of plaintext whose corresponding ciphertext satisfies some given condition. This step outputs a message, say M. Now in the second phase, assuming that M and M XOR alpha dash is a very good pair, we apply Grover's again over all 2 to the power n subkeys to obtain the subkey which decrypts the corresponding ciphertext to the required difference. And at the last, we try to recover the remaining m-1 round keys by proceeding as in step 2. And in SPECK, if we can find m round keys, we can retrieve the complete secret key. Now, the complexity of the first step is these many encryptions, SPECK encryptions, because we have 2 to the power p by 2 SPECK encryptions plus a decryption of 1 round here. So we have these many SPECK encryptions. The second step finds the round keys after 2 to the power n by 2 iterations. So the computation time of this step is these many SPECK encryptions. And the computation time for the third step is almost same as the second step, but m-1 times. So in total, we achieve these many SPECK encryptions as the computational complexity with c is equal to pi by 4. Now we implement the last round attack on IBM-Q. We have made the following assumptions: that we have a 5 round differential alpha dash to beta dash with p is equal to 4. We implement the key recovery on 6 rounds. Let the difference in the ciphertext after 6 rounds be denoted as this. The secret key is considered to be this, and so the round keys are as follows. So we'll try to retrieve the 4th and the 5th subkey. That is, in phase 2 the output should be 0 1 1, and in the phase 3 the output should be 1 1 0. So we first implement phase 1. We try to search for plaintext pairs whose corresponding ciphertext satisfies the following 2 properties: this, and 1 round decryption leads to the difference, this. The pair obtained is as given here, 0 1 1 0 1 0, and since alpha dash is this, so the plaintext pair for the second phase is this. Now we use this plaintext pair which we have obtained in the second phase. So first what we do is we find what are the corresponding ciphertexts of this plaintext, and we have obtained it to be this. Then we apply Grover's to search for the key which decrypts this pair so that they form the difference this, and as expected the output is 0 1 1. In the third phase, the ciphertext pair was here. We decrypted this 1 round using the key which we had found above, and we find this. Now using this, we search for all the subkeys which will decrypt this 1 round to this pair difference, to this difference. As expected, the output is 1 1 0. Now the resource estimations. Phase 1 makes 2 to the power p by 2 iterations of these of r plus 1 round spec and 1 round decryption. So we have these many rounds, spec rounds. In spec 2, so this step will have 2n measurements and requires these many qubits and 2n classical bits. Phase 2 partially decrypts 1 round and makes measurement of the round key. So this step has these many 2 to the power n by 2 iterations of 1 round spec and has n measurements and will require these many qubits. Phase 3 is a repetition of phase 2 for m-1 times and the resources required can be computed similarly. So in total, to construct the entire circuit for this last round attack, we will have these, the number of qubits required will be this much, classical bits would be this much, measurements would be 2n plus mn, as many measurements so many classical bits, and the gates which will be required to implement 2 to the power p by 2 r plus 2 plus 2 to the power n by 2 by m round updates and 2 to the power p by 2 r key expansions. So we have these are the resource estimates required. These estimates are based on the differentials computed by F. Abed et al. In their paper Differential Cryptanalysis of Reduced Round Simon and SPECK, which was published in FSE 2014. So in conclusion, we perform quantum cryptanalysis on lightweight cipher SPECK. We analyze the exhaustive key search and differential cryptanalysis in quantum framework exploiting Grover's algorithm. For both the cases, we estimate the quantum resources required for implementing the attacks. Experiments are performed in IBM Q environment considering a toy version of the cipher. Thank you.